So group 9, you can start, or group 10, any one of the groups. Okay.
Yes, ma'am. Group 9 is starting. Just is my screen visible?
Yes, 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 yes.
Okay, I'll begin.
Sure.
So our paper was towards the next generation of recommender systems, and group members are Anuj, myself, that is B22I061, and Abhinav Swami, B22I003. So we all have somewhere in our lives reaped the benefits of recommender systems, like when we use Netflix or when we use Amazon or whatever, like the recommendations that we get, maybe movies, maybe items to buy, all those are from recommender systems. And but let me just give you an idea of why this motivation for recommender systems came. So a very simple example would be like, let's say there is a retail store, and in a retail store, the shelf space is a scarce commodity. Like a retailer can only stock the popular items; they cannot stock a lot of the non-popular items. And this is sort of a long tail distribution as seen in this graph. So what happened was, because of the internet, because of advent of platforms like Amazon, shelf space no longer became a scarce commodity. Like on Amazon, you have a plethora of items, and like, so the motivation is that as there are more choices, it necessitates better filters. We need better filters. So a good example of this is that when Touching the Void, it is a book which came out in 1988. It was not a bestseller back then, but in 1997 another book came out, Into Thin Air, which became a bestseller. And what happened was, Amazon made the correlation that some of the people who had bought Into Thin Air had also bought Touching the Void. So it started recommending Touching the Void to those people, and because of that, it also became a bestseller. So because of a recommender system, a book became a bestseller. So this is the motivation. So there are different kinds of recommendations. It can be editorial and hand curated. It can be simple aggregates like how we see on Netflix top 10 in India. So these are just simple aggregates who are most popular. And there can be tailored to individual users like we see recommended for you. So these are for individual users. And there are different types of recommender systems, content-based systems, there are collaborative methods, and there are hybrid methods. So let me begin with content-based methods. And before I begin, I would like to just reference the mining of massive data set scores from Stanford. A lot of these images are taken from those slides. So this image gives a good idea of what is the plan of action in a content-based method. So what happens is, a user has watched some movies, or let's say a user likes certain movies. Items in this case are movies. So let's say every movie may have some item profile, and based on those item profiles, we do some sort of aggregate and build a user profile. And with that user profile, we check our catalog of items, and we try to find some similarity between that user profile and the item profiles of the items in the catalog. And the ones which are most similar get matched and get recommended to us. So this is a simple idea. So a more detailed um explanation would be like, for each item, like let's say for movies, the movie profile would be a set of features like author, title, actor, director. For images and videos, it may be metadata and tags. For people, it will be set of friends. So it is convenient to think of the item profile as a vector. And a special case is text features, like in a document. The important features or important words can be calculated using a very common heuristic known as TF-IDF, which is term frequency inverse document frequency. So basically, the formula can be seen that Fij is the frequency of term or word I in doc J. So term frequency is frequency that term I appears in document J divided by maximum number of times that term appears in any document. And IDF is log of n by nj, where n is the total number of docs and ni is the number of docs that mention the word I. So the relevance of IDF is, let's say we have the word the. Now the may be appearing in practically every document, so it may not be such an important word. So what happens is ni converges to n and IDF converges to 0. So that is why we take a multiplication of TF IDF. So yeah. And then the user profiles. So user profiles can be computed using a very simple average of the item profiles, or there may be some normalization. So these are some very simple examples from the slides of the course. Like one of the example is like, let's say a user has rated actors A movies as 3 and 5 stars, and actors B movies are rated 1, 2, and 4. So we can observe that 1, 2, and 4 for actor B seem less than actors A's 3 and 5. So 1, 2 may be some sort of negative rating, like the user may not like actor B. So what we do, we just normalize the ratings. So that captures the fact, as you can see in the calculation, that actors B's ratings come out to be -2, -1, and +1. And in the user profile, the weight for actor B comes out to be -2/3. And the final recommendation process is, as I said, taking the similarity. Most common example is cosine similarity. And yeah, so TF-IDF and cosine similarity are heuristic-based approaches. There may also be model-based approaches, like there may be Bayesian classifiers. Like we may use some sort of naive Bayes classifier or something, like, let's say, it may assign probabilities, like a user has watched movies of actor A. User has watched 5 movies and actor A was in 2 of them. So probability for actor A would be 2 by 5, and many such probabilities. And there may be machine learning algorithms like neural networks, which tend to find patterns based on past interactions and item attributes to predict items that the user may like. Machine learning, primarily it is used for observing complex patterns which may not be as effective in heuristics. So yeah, the limitations are finding the appropriate features are hard. For example, in images, movies, and music. And another is over specialization. Like we are only using other items. We are not even considering other user profiles. We are only considering item profiles. So it never recommends items outside users' content profile. And but people may have multiple interests, so this is an issue. And there is a cold start problem. So that basically means like a new user may not have rated any movie. So how to compute the user profile for him? So that is an issue. But this is not the issue for a new item. The new item already has the features. So the item profile is already created. So that we only have an issue for new users, not for new items. So there is another method which is collaborative methods. So collaborative methods now takes into account similar users. Like but in this case, we have a utility matrix. It is not based on user profiles. We have utility matrix. So there are two types of basically collaborative filtering, like user-based filtering. It finds user which are similar to our target user and recommends the items that they like. And item-based is finds items similar to what the target user has liked and recommend those. So yeah. So there are two types of algorithms: memory-based or heuristic-based and model-based. So this is how a utility matrix looks. The phi symbol, it means that Bob has not rated the movie K-Pax. Similarly, Cindy has not rated the movie Notorious, and David has not rated Life of Brian. So the core algorithm in memory based, as we can see, it is a sparse user item matrix because not every user will rate every movie. So what we do is to find the unknown rating, the RCS, which is for user C and item S. It is usually computed as an aggregate of ratings of some other, usually the n most similar users for the same item S. So yeah. So some examples of those aggregate functions are which are used to compute unknown ratings. It can be a simple average, as seen in A. It is a simple average. Here, C cap, C dash belongs to C cap. C cap is the set of the most similar users who have rated item S, and from those we pick the most. Those are the most similar, so we just average their ratings. And but this is very simple. So one change that we do is we take weighted sum. So weighted sum, what it does is it takes the similarity between the user, like our target user, and C cap, which is the most similar user to our user profile, and it takes the similarity between them and weighs the ratings of C cap with that. So basically, and we use a normalizing factor K, whose formula can be seen here. And again, there is a problem with that also. It does not take into account that different users may have a different rating scale. Some may be very lenient. Some may give the movies they don't like a three-star rating, where some may only give a 4-star rating to the movies they like. So that fact needs to be accounted for. So that is how C takes into account, like it normalizes the ratings of our similar user profile C cap, and then it multiplies with similarity, and in the end, it adds the mean rating of our target user. And the similarity computation, the similarity that we were talking about here, the similarity computation, it is a simple distance measure. It acts as a weight. The more the similar user C and C dash are, the more the weight rating R C cap S will carry in the prediction of RCS. So basically, it is a heuristic that may be considered as that it finds closest peers or nearest neighbors. So the most common approaches are correlation. This is what is known as Pearson correlation, and this is the common cosine similarity approach. So yeah, this and in item collaborative filtering, the other approach that I was talking about. So for each item, like for every item, we find other similar items, and for that, for the rating for item I is based on ratings of similar items. Like it can be seen in the formula, this formula. Here we have only exchanged, you can say, the rows and columns of our metrics. Earlier, the rows of our metrics were users, where we were finding similar users who had rated movies. Here we are finding similar movies that are rated by the user. So that only that is exchanged, rest all remains the same. And this is another example, so this can be checked out. Yeah, so another model based approach for collaborative filtering is that it is a probabilistic approach, and it calculates an expectation. Here E stands for expectation. So E computes the, as seen in the formula, its interpretation is that the rating values are integers between 0 and n. This probability expression is the probability that user C will give a particular rating to item S. Like RC is equal to 0 means user C has given a rating of 0 to item S. Yeah, and that depends on user's rating of previously rated items. S dash belongs to SC. This stands for the items that the user has previously rated. And then there are further approaches, cluster models, and Bayesian networks. So the limitations still stand the same. Like there is a new user problem. So new user, as we said, we have a sparse metric. So even the new user, as soon as he comes into the database, a user won't rate the movies. Like a new user would not have rated any movies. So that is an issue. And like I pointed out in content based, we did not have the problem of new items. Here we do have the problem of new items, because until enough users have rated a new item, it remains under recommended. And for both of these, we can use hybrid systems which incorporate attributes like content based filtering along with collaborative. And another issue is sparsity, as spoken earlier, like users don't rate items. So yeah, one solution is dimensionality reduction, a very common solution actually. It uses singular value decomposition. It is a very common approach which approximates a sparse matrix if we have one with lower rank representations. And then we, like I said earlier, to mitigate these issues, we may consider using hybrid approaches. So what do these hybrid approaches mean? Is that some of those, they combine results from both methods. Let's say we use content based and collaborative both, and we perform a linear combination. Other thing we can do is feature augmentation. Like in content-based methods, we use techniques from collaborative-based filtering, and in collaborative-based, we use content-based. For example, like in collaborative-based, we do not consider user profiles. Maybe we can do that so it may be better. And switching it alternates between methods based on context. Yeah, for these limitations are like it will become complex as we are considering multiple recommendation methods, and the computation cost would be more as if we consider a linear combination of many recommender systems. That then the cost will increase. So this is a very concise summary of what I have spoken till now, like content-based methods, collaborative, hybrid, and their heuristic-based techniques, model-based techniques, and so on. So, yeah. Now we need to talk about how we can extend the capabilities of our recommender systems. So, like as spoken earlier, collaborative filtering ignores the user profiles and item profiles. So generally, our rating estimation procedure, like when we extrapolate the rating for unknown ratings, that function is given by Rij. If Rij not equal to 5 means if the user has already written movie J, then we need to do nothing. But equal to 5 means user I has not written movie J. Then we use some function Uij, which is a function of C vector means the user profile and S vector means the item profile. And that utility function, it includes various heuristics, nearest neighbor classifiers, decision trees, spline methods, radial basis functions, etc. etc. Another common approach is a radial basis function. So what radial basis function does is it is used in approximation theory. It estimates unknown functions, and let's say we have a set of points x which goes from x1 to xn, and known function values for those points. So for new points, let's say we get a new item profile, and we have known item profiles. So for approximating that, we can use an RBF function where phi is our RBF function, and that input to that function is the norm between the known points and the unknown point. Like we need some sort of closeness between the unknown and known points. Like if the new point which comes, it is closer to known points, then the rating should be closer. And if they are far apart, then ratings should be different. And these are some common examples of RV functions. A very important point is that phi is positive definite function. And these are the common examples. And yeah. One challenge is that we not cannot, but it is difficult to adapt RVS for non-Euclidean recommendation space. And yeah, another thing, like when we use collaborative filtering, we are using a user cross item matrix. So, but there can be more context in our recommendation, and like there can be more dimensions such as time, location, or company, which enhances context awareness. Like a very good example for this is that there are relevant dimensions like what and whom. So, what item genre means what I am recommending. I am recommending an item to a user. What is the context of the item? Item genre. For whom I am recommending the item to a user. User's context is time and location. A good example is like for a weekend night movie with friends, the system can recommend different than for a weekday alone. And yeah, this is the mathematical formulation. Like rather than in a regular context, it would have been D1 cross D2, which would have been user cross item, but we extend it till n, where we take n different features, which are also the context for context. Yeah. So we can use hierarchical Bayesian model extension. Yeah. And another thing is multi-criteria ratings. Now, simply one cannot rely on an overall rating. Let's say I have a user who prefers ambience of a restaurant more than the service or more than the food quality, let's say. So there may be different criteria. But generally, we only take one criteria, which is the, I think, overall rating. We use single criterion ratings. So in order to accommodate for multi-criteria, there are some approaches. There is something known as Pareto optimal solutions. And this optimizes across all criteria without trade-offs. Then there is a linear combination which combines all the criteria into a single score. Uh, then there is a primary criterion with constraints. We can treat one criteria as primary. Let's say in this example, our objective is to maximize food quality, subject to decor and service. So sorry. So decor, which is denoted by DC of R, should meet a minimum requirement, which is delta C, and service should also meet a minimum requirement, which is gamma C. So this is an example of primary criterion with constraints. And there is also sequential optimization, which optimizes each criterion individually and converting other optimal solutions to constraints. So yeah, the missing ratings is a common challenge till now. And yeah, so future directions may include finding Pareto optimal solutions as this identifies optimal solutions across all criteria. So yeah. And there is an issue in our recommender systems, like the factor of intrusiveness. Like for example, even earlier on, Netflix used to do this in very early years, not recently, but they used to ask users to rate movies or rate genres, and it used to be a very extensive list. So this used to be very intrusive and time consuming for users. So the solution for this is we can use some sort of proxies which just estimates the user behavior based on how they interact with the platform. And we can also make an optimal ratings request, like rather than having a very elaborate form, we can have a smaller form, and like we can find an optimal uh, define an optimal number of initial ratings. And active learning means to selectively request ratings that maximize model improvement. Then there is one another thing. There is flexibility in recommender systems. So solutions have been made for this. Like the issue was that recommender systems are inflexible. Like they always provide vendor defined recommendations with limited user customization. Like there is no user input in getting what they want as a recommendation. So a few solutions is a recommendation query language. It is an SQL like language. This is the example for this which was given in the paper. So yeah, and aggregated recommendations. It uses an OLAP-based approach for recommending categories. So OLAP is generally used for categorical recommendations and also. And in order to measure the effectiveness of our recommendations, common metrics like accuracy, mean absolute error, RMSE, precision recall, as measured very common, which are generally used to evaluate models also. So ROC curves. And some advanced metrics which may be business-oriented metrics like ROI and customer lifetime value. And uh, like modern recommender systems nowadays, they focus on explainability. Means like a very simple example, Spotify. Like if I listen to some particular category of music, or maybe to some particular artist's music or songs, then it recommends me and it says inspired by your recent listens. Or on Netflix, like because you watched this movie, you were recommended these movies. This is explainability. And there is trustworthiness. So building user trust is a priority, and recommendation should align with user intentions and should be free from biases. So LinkedIn, for example, incorporates trust-focused AI principles to avoid the bias in job recommendations. So yeah, coming to the conclusion, there have been significant advancements over the past years. Recommender systems have evolved from very basic collaborative and content-based methods to sophisticated hybrid systems, and they can consider vast data sets, user context, multiple criteria, as spoken earlier. And the key issues was an area of explainability, trustworthiness, scalability, and privacy. So these are a few examples of techniques such as natural language explanation, fairness-aware algorithms, cloud-based scalability, and privacy-preserving methods. And the next generation focus is to make flexible, transparent, and user-centric systems, which integrate advances in AI to enhance accuracy, personalization, and user satisfaction. And for broader application potential, recommended systems are poised to become more effective and impactful in fields beyond the traditional e-commerce and entertainment, and to support a wide range of user needs in education, healthcare, social media, and beyond. Thank you.
Very good. That was a very nice presentation.
Thank you.
Very nice indeed.